Welcome to the study of energy flow in chemical reactions. Enthalpy is a thermodynamic quantity that represents the total heat content of a system at constant pressure. Calorimetry is the science of measuring that heat flow. Together, they form the foundation of thermochemistry, allowing us to quantify exactly how much energy is absorbed or released during chemical processes. From the digestion of food to the combustion of fuels, from industrial chemical synthesis to biological metabolism, understanding enthalpy and calorimetry gives us a powerful quantitative tool for predicting and measuring energy changes. In this presentation, we will explore the definition of enthalpy, learn how to calculate enthalpy changes, understand the workings of calorimeters, apply Hess's law, and work through detailed problems and quizzes to master these essential concepts. Enthalpy is defined as the sum of the internal energy and the product of pressure and volume. The mathematical expression is H equals U plus PV. Since most chemical reactions occur at constant pressure, open to the atmosphere, the change in enthalpy, delta H, equals the heat absorbed or released. A positive delta H indicates an endothermic process where the system absorbs heat. A negative delta H indicates an exothermic process where the system releases heat. Enthalpy is an extensive property, meaning it depends on the amount of substance. Standard enthalpy changes are typically reported per mole of reaction. The SI unit is the joule, though kilojoules are more commonly used in chemistry. Enthalpy values for elements in their standard states are defined as 0 by convention, providing a reference scale for all compounds. A thermochemical equation is a balanced chemical equation that includes the enthalpy change, delta H. For example, the combustion of methane, CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O liquid, with delta H equal to negative 890 kilojoules. The negative sign indicates the reaction releases 890 kilojoules of heat per mole of methane combusted. The physical states of reactants and products are crucial because enthalpy depends on state. Water liquid and water gas have different enthalpy values. The enthalpy change is proportional to amount. If we double the reaction, delta H doubles. Reversing a reaction flips the sign of delta H. When writing thermochemical equations, always include the states and the delta H value. The standard enthalpy change, delta H naught, is measured under standard conditions: 1 bar pressure, 298 Kelvin, and 1 molar concentration for solutions. Calorimetry is the experimental technique of measuring heat flow during chemical or physical processes. The device used is called a calorimeter, an insulated container that minimizes heat exchange with the surroundings. The fundamental principle is that heat lost by the system equals heat gained by the calorimeter and its contents. This is conservation of energy. The key equation is Q equals mc delta T, where Q is heat energy, m is mass, c is specific heat capacity, and delta T is the temperature change. Specific heat capacity is the amount of heat required to raise 1 gram of a substance by 1 degree Celsius. Water has an exceptionally high specific heat capacity of 4.18 joules per gram per degree Celsius, making it excellent for calorimetry. Calorimetry allows us to determine delta H for reactions by measuring temperature changes in a known mass of water. Two common types of calorimeters serve different purposes. A coffee cup calorimeter, also called a constant pressure calorimeter, is a simple polystyrene cup open to the atmosphere. It measures delta H directly because the reaction occurs at constant pressure. It is ideal for solution-based reactions like acid-base neutralization. A bomb calorimeter, or constant volume calorimeter, is a sealed steel container that withstands high pressures. It measures the heat of combustion or reactions involving gases. In a bomb calorimeter, the measured Q is delta U, the change in internal energy, not delta H. The conversion is delta H equals delta U plus delta nRT, where delta N is the change in moles of gas. Bomb calorimeters have a known heat capacity, Ccal, that must be calibrated using a standard substance like benzoic acid. The standard enthalpy of formation, delta H F0, is the enthalpy change when 1 mole of a compound forms from its constituent elements in their standard states. The conditions are 298 Kelvin and 1 bar pressure. For example, delta H F0 of CO2 gas is the enthalpy of solid carbon plus oxygen gas yielding carbon dioxide. Elements in their standard states have delta H F0 equal to 0 by definition. The standard enthalpy of reaction can be calculated using the formula delta H0 of reaction equals sum of coefficients times delta H F0 of products minus sum of coefficients times delta H F0 of reactants. This powerful relationship allows us to calculate delta H for any reaction if we know the delta H F0 values of all species involved. Tabulated values of delta H F0 for thousands of compounds are available in reference sources. This method is often more practical than measuring every reaction directly. Hess's law states that the enthalpy change for a chemical reaction is the same regardless of the pathway taken, provided the initial and final states are identical. This is a direct consequence of enthalpy being a state function. If a reaction can be expressed as the sum of 2 or more steps, the total delta H is the sum of the delta H values for each step. This allows chemists to calculate delta H for reactions that are difficult or impossible to measure directly, such as the formation of carbon monoxide from carbon and oxygen. To apply Hess's law, write the target equation, manipulate known equations, reversing flips the delta H sign, multiplying multiplies delta H, cancel common species, and sum the remaining delta H values. This algebraic approach is one of the most powerful tools in thermochemistry. Calorimetry has wide-ranging practical applications. In food science, bomb calorimetry determines the energy content of foods. The calorie on a nutrition label is actually a kilocalorie, equal to 4.184 kilojoules. In materials science, differential scanning calorimetry, or DSC, measures phase transitions, glass transition temperatures, and polymer curing. In biochemistry, isothermal titration calorimetry, or ITC, measures binding affinities between molecules. In environmental science, calorimetry helps assess the energy content of fuels and biomass. Industrial calorimetry monitors exothermic reactions in chemical plants to prevent runaway reactions. The versatility of calorimetry lies in its direct thermodynamic measurement. Modern calorimeters can detect temperature changes as small as 1/1,000,000th of a degree Celsius. Quiz question 1. Which statement best defines enthalpy H? Option A. H equals U minus PV. Option B. H equals U plus PV. Option C. H equals U divided by PV. Option D. H equals U times PV. Study the options on screen and select your answer. The correct answer is B. Enthalpy is defined as H equals U plus PV, where U is internal energy, P is pressure, and V is volume. At constant pressure, the change in enthalpy equals the heat absorbed or released by the system. This makes enthalpy especially useful for studying chemical reactions that occur in open containers. Quiz question 2. In the equation Q equals mc delta T, what does C represent? Option A, the heat capacity of the calorimeter. Option B, the specific heat capacity. Option C, the molar enthalpy of the reaction. Option D, the temperature in Celsius. Study the options on screen and select your answer. The correct answer is B. The specific heat capacity, C, is the amount of heat required to raise 1 gram of a substance by 1 degree Celsius. Water value is 4.18 joules per gram per degree Celsius, one of the highest known. This makes water excellent for calorimetry and cooling systems. Quiz question 3. A bomb calorimeter measures which quantity directly? Option A, delta H, the enthalpy change. Option B, delta S, the entropy change. Option C, delta U, the internal energy change. Option D, delta G, the Gibbs free energy change. Study the options and select your answer. The correct answer is C. A bomb calorimeter operates at constant volume and measures delta U directly. To get delta H, we use delta H equals delta U plus delta N RT, where delta N is the change in moles of gas. Quiz question 4. According to Hess's law, if a reaction is reversed, what happens to delta H? Option A, delta H becomes 0. Option B, delta H is doubled. Option C, delta H changes sign. Option D, delta H is halved. Study the options and select your answer. The correct answer is C. Reversing a reaction changes the sign of delta H, but not the magnitude. Enthalpy is a state function, so the difference between products and reactants is the same, regardless of direction. Quiz question 5. Standard enthalpy of formation for an element in its standard state is what? Option A, always positive. Option B, always negative. Option C, 0 by definition. Option D, equal to its heat capacity. Study the options and select your answer. The correct answer is C. By convention, delta H F naught of any element in its most stable form is defined as 0 at 298 Kelvin and 1 bar. This provides a consistent reference for calculating reaction enthalpies. Problem 1. Calorimetry calculation. A 250-gram sample of water at 18.5 degrees Celsius absorbs 4.50 kilojoules of heat. We need to find the final temperature. Water-specific heat is 4.18 joules per gram per degree Celsius. Step 1. Convert kilojoules to joules. 4.50 kilojoules times 1,000 equals 4,500 joules. Step 2. Apply the calorimetry formula. Delta T equals Q over MC. Delta T equals 4,500 over 250 times 4.18. Step 3. Calculate delta T. 4,500 divided by 1045 equals 4.31 degrees Celsius. Step 4. The final temperature is initial plus delta T. 18.5 plus 4.31 equals 22.8 degrees Celsius. The answer is 22.8 degrees Celsius, rounded to 3 significant figures. Since water absorbed heat, Q positive, this is endothermic. Problem 2. Bomb calorimetry. A 0.500 gram sample of naphthalene is combusted in a bomb calorimeter with heat capacity 5.12 kilojoules per degree Celsius. Temperature rises from 22.00 to 26.08 degrees Celsius. Step 1. Temperature change. 26.08 minus 22.00 equals 4.08 degrees Celsius. Step 2. Heat released. Q equals negative C cal times delta T. Negative 5.12 times 4.08 equals negative 20.89 kilojoules. This is delta U. Step 3. Moles of naphthalene. 0.500 divided by 128.17 equals 0.00390 moles. Step 4. Delta U per mole. Negative 20.89 divided by 0.00390 equals negative 5,356 kilojoules per mole. Step 5. Combustion produces 10 CO2 and 4 H2O from 1 naphthalene plus 12 O2. Delta N gas equals 10 minus 12 equals negative 2. Delta H equals delta U plus delta N RT. Negative 5356 plus negative 2 times 8.314 times 10 to the negative 3 times 298 equals negative 5,361 kilojoules per mole. The answer is delta H, approximately negative 5,120 kilojoules per mole, highly exothermic. Problem 3. Enthalpy of formation. Calculate delta H naught for the combustion of propane. C3H8 gas plus 5O2 gas yields 3 CO2 gas plus 4 H2O liquid. Given delta HF naught values, propane negative 103.8, CO2 negative 393.5, water negative 285.8 kilojoules per mole. Step 1. Sum of products. 3 times negative 393.5 plus 4 times negative 285.8. Negative 1,180.5 plus negative 1,143.2 equals negative 2,323.7 kilojoules. Step 2. Sum of reactants. 1 times negative 103.8 plus 5 times 0 equals negative 103.8. Step 3. Apply the formula. Delta H equals product sum minus reactant sum. Negative 2,323.7 minus negative 103.8 equals negative 2,219.9 kilojoules. The answer is negative 2,220 kilojoules. Propane combustion is highly exothermic. Problem 4. Hess's law. Calculate delta H for the formation of NO gas using Hess's law. Equation 2. 2NO plus O2 yields 2NO2 with delta H negative 114.1 kilojoules.